Conservation of momentum. Okay, so we're back in the last hour of this. Now we see the top of the mountain. It's there, and you're just with your nails climbing up the last little bit, running out of oxygen, and so on. Okay. So let's recall that we had our. I'm going to write down, and I hope that you remember our equation of conservation of momentum for a control volume. And the most general one, before we simplified to 1D, steady flow, and so on, was this integral equation that was the sum of forces in the control volume. I hope it will ring a bell at least. We had the partial derivative with respect to time in the control volume of velocity rho dv, with this v being volume. Then we had the integral across the control surfaces, the flux terms, v, rho, and this is v dot n, where n is the outward facing normal and differential of area. We simplified our lives quite a bit by constructing our control volume such that the control surfaces were perpendicular to the velocity. Of course, this integral is only not zero where the velocity is not zero. We consider velocity to be uniform, and so it came out of the integral, steady flow, and this was simplified considerably, right? But now I'm putting the whole equation there. So now we're going to apply, we're going to consider a infinitesimal fluid mass. Infinitesimal, again, control volume. For an infinitesimal control volume, where we're going to look at a differential of force, and we're going to say that differential of force for that little small control volume is going to be dm, the differential of mass, times the acceleration. So just Newton's law applied to the little small mass dm. So let's think about a little bit about what types of forces could be involved first. The types of forces that you could have in this case are, for a fluid, weight, normal forces, and shear forces, tangential, right? So we're going to consider the weight first. The easiest one is a differential of force called weight is just dm times g, the acceleration of gravity. Then we have some surface forces which could be normal or tangential. Normal is pressure, but we're going to write them now. Let's see, imagine that we have a small surface here and we're looking at a little patch of area, dA, this is dA, and we have perhaps a normal force. This is normal to the differential of force normal to the surface. We have then perhaps two components of tangential forces. Let's call them just F1 and F2, dF1 and dF2, which are the two tangential forces in two orthogonal directions. So Fn is the normal force to the area. F1 and F2 are forces parallel to the area but orthogonal to each other. That's all that we have. So we'll use the concept of stress in general in fluids. Normal stress, we use the symbol sigma for normal stress. Let's use the little n to indicate normal, and it's going to be the limit when this small area tends to zero of the differential of force in the normal direction divided by the differential of area. Force divided by area is stress. The tangential stress, or shearing stress, we have the two components that are, we use tau for shear. Tau 1 is equal to the limit when the differential of area tends to zero of this force F1 divided by the area, and tau 2 is equal to the limit delta A tends to 0, dF2 over the area, force divided by area. Now, we do usually make reference to a coordinate system to apply a notation. For all the possible shear and normal stresses that could exist on a small volumetric cube like this, okay, where we have, so this is very small, although I've drawn it big for our understanding, but it's going to be an infinitesimal small little area. And so we have, suppose in this wall we could have two tangential forces and one normal. So this is the notation that we use for these guys are the following. So this we're going to go call sigma xx. This we're going to go call tau xy. And this one we're going to call tau xz. And I'll explain in a minute. So the plane that we're looking at, this is the plane parallel to the YZ plane. This face is parallel to the YZ plane. YZ is correct? No, it's not. What am I doing? Oh, I changed around my, sorry about that. I've changed around my axis, and I'm going to have to be consistent with that because otherwise it'll be a mess. I'm so sorry. So erase that please and write it so that it makes sense towards my drawing. I've made it like this, Z, X, Y. So now that's why it is actually parallel to the YZ plane. So I've just turned around my axis. It's still properly, right-hand rule like it should. So in this, the normal stress, so we have these three stresses, sigma xx, tau xy, and tau xz. And you notice that the first subscript is always x. This is going to be our notation because on the YZ plane, the normal vector points in the x. So the first subscript refers to the normal, the direction of the normal on that face. All of those first x's. First subscript equals the direction of the normal vector, which is x for that face. The second subscript refers to the direction of the vector, of the stress vector. So sigma xx, the outward facing normal, is in the x direction. The stress is also in the x direction because it's the normal stress. This one, the second subscript points in is y because the vector points in the y direction. This one, the second subscript is z because it points in the z direction. Okay, that's going to be our agreement to be able to write all of these vectors. And there's also a sign convention. Let's see, how do I say? If the outward normal points in the negative coordinate direction, then the stresses are considered positive when they also point in the negative direction. So let's be clear about that. I'm going to make a big picture here. It's the only way I can think of it. Like, I'm just going to look at the now I'm going to look at the other face, the negative one, which is that face, right? Behind there. That's the negative from the cube I drew before. And my coordinates are still the same. And so now I have, as stress vectors, I'm going to point downwards in the negative y direction, and I'm going to point backwards there in the negative z direction, and that is sigma. So these are the ones that are going to be considered positive, because since the normal points in the negative direction, all the stresses that point in the negative direction, I'm going to keep a positive sign with it. Okay, I'm going to keep these. That's the sign convention that is used. X, Y, and this is tau. So it's still X, but it's negative, right? Minus X. It's still X, the normal to this wall, to this face, and this is Z. These are the positive stress vectors, the ones I've drawn here. They're on this back wall. This is the sign convention. So if the outward normal points in the negative, coordinate direction, as shown in this picture, the stresses that are considered positive point also in the negative coordinate directions. So this is we drew before the positive face, if you will, and now we've drawn the negative face, and we've always pictured the stresses in what would be considered the positive direction. So now we're going to be able to use all of these conventions to do a complete force balance on a infinitesimal cube of fluid. And we can call each phase what it needs to be, and so on. Every single stress can be considered. Just bear with me a little longer, okay? Don't give up. Some of you are looking like, oh no. But we're almost there, okay? And this is the only time I'll make you go through this, I promise. So I'm going to make it rather large, but it's supposed to be an infinitesimal volume of fluid, so that I can draw all the stresses here. Actually, I'm just going to draw the ones that are pointing in the x direction to make it easy. So pointing in the x direction, we have this one, we have this one, we have on the top wall, I'm going to change colors and let's see how am I going to do this. In the top, I'm use the red for the top. This is the top wall, right? And in the top wall we have, so then we have a stress there, and then we have one at the bottom as well, okay, pointing the other direction. And I'm going to do a third color here. Fortunately I have three colors. One is going to be here, and I've drawn them always in the positive direction. On this face, the front face, I have one here and one in the back. So this one is in the back face, right? It's hard to draw this in perspective, I hope, but we've considered in the red, top and bottom face, in the blue, the two ones that are parallel to the paper, front and back, and the greens are the normal ones on the side walls, and these are all of the stresses in the x direction. Yeah? And here is where we apply our, the variation in space of these possible stresses, and with respect to the center. In the center of this control volume, we would have a value, and we're going to move, say, this is going to be, where's my axis again? Let's not be, so x, y, and z. So this side is delta x, and this side here is delta y, and this one here, oh, I've got it, that one, so this is delta y, correct, and this is delta z, right. Okay, so this, let's do this one, the green here. This one is sigma xx. But we've moved in the negative direction by delta x half. I'm going to make a little bit space here to write that one. Delta x half. So minus the partial derivative of sigma xx with respect to x times delta x half is the first term of the Taylor expansion. So that's the variation of sigma xx in the minus x direction, right? And this multiplied by the area. What's the area of that face? dy dz, thank you. Sorry, forgive me, I didn't... This negative sign? This term? The whole thing, what about it?
It's just for the 1 point.
Just for the 1 point in there. The 1 point in the other direction will be sigma xx plus variation of sigma xx with respect to x times delta x half. dy dz. Yes?
When you write that kind of d, what's different about that from like when you do the partial?
This is a partial. Oh, this one?
Yeah, like the...
because this is just oh, I'm sorry. Oh my goodness, look at that. Oh no. Because this is just I'm just calling this distance delta x, and it's just a distance. It's a small distance. I could call it delta x like that. It would be this, just, but it's not any differential operator. It's just a small distance. Okay, so the same applies to the blue and the red ones. The red here on top is going to be that's a tangential stress on the top wall, and what is the outward normal of that wall? What coordinate direction is it? Y. So the first subscript is y. What direction is the stress pointing? X. The second subscript is x. Good? This is the top one, the red. The top. But we've moved from the center by plus y, so it's a plus variation of the same stress, tau yx, with respect to y dy half. And the area of the wall is dx dz. Okay, the bottom one. This one down here. It's in the bottom wall, sorry, the bottom face. What is that? The same tau yx, but minus the variation of tau yx with respect to y and dy half, and the same area, dx dz. Yeah? Now the blue ones. So now all of the stresses we're showing in the positive direction. Okay, the blue one, this guy over here. Don't have there, that one. So what is the outward facing normal? Z. Good. So it's tau z, and it's pointing in x, tau zx, minus the variation of tau zx in which direction? What's the variation from the center of the box to dz times dz half? That's the distance we've moved, the first term of the... Because from the center of the box, we moved to that face in the z direction. From the center to the... And the area? dx dy. Okay, now we can do the one in the back, here, the back face. And that is the same stress component, tau zx, but plus, because we're moving the positive. Oh no, did I get the signs wrong? I got the signs wrong. This is plus, and this is minus. I got the signs wrong. In the minus now. This one moved in the minus direction. d tau zx, dz, dz half, and d x and y. We have all the forces now in the x direction. We can do balance of forces in the x direction if we put all of these things together in one. We can do the sum of forces in the x direction, okay? And we're almost there, because once we have the x direction, then we can just write the other one directions immediately, because they're going to be similar, or you at least see where they all come from. So I'm going to take a screenshot of this page in case we need to see it again. Yes, question? This one? dy dz? Oh, this is supposed to be a different sort of shape. See, is that the I'm sorry. It's just my sloppiness on writing that. It's just, yeah. Thank you. Thank you indeed for pointing out my sloppiness, so I can improve. I don't apologize. I improve. And for the geeks out there, that's a line from Xena the Warrior Princess. When she tells the sidekick, which I don't remember her name, don't apologize, just improve. It's the best line in the show. Okay. Are we ready? We put all these together in one equation and we have balance of forces in the x direction? Good. Oh, look, I had extra slides for those things. Equations of motion. Oh, we're almost there. Equations of motion, the next slide. Okay, so the sum of forces in the x direction. Oh no, we're running out of time. We'll make it. Somebody's looking at the time in there. All right, so in the x direction we have, let's see. When we put together the terms that have sigma xx, you see that the, they're pointing in a different direction, right? One was negative, one was positive. So when I subtract them, the actual one that has sigma xx is going to cancel out. Let me pull out. See, there was a reason to have that snapshot. Okay, this one points in the negative. That one points in the positive direction. And so when I add these out together, can I do this? Click with the mouse, yes. When I put these two together with the right sign, this will cancel out. And I'm going to have this with the half, but they're going to add, so the half is going to cancel out, you see? And so I'm only going to have left, basically, the partial of sigma xx with respect to x times, well, it's a 2, and then delta x half, and so the 2 will cancel out, and then I will have dy dz, so I have the complete volume here, and I only have the partial of sigma xx times the volume. Yeah? The same will happen to the other terms. Because they point in different directions, the first order term will cancel out, the other two will have, well, so these two, the red ones, right? The first order term will cancel out because they point in different directions. the negative sign will flip, and that means that I'm going to have a 2, which cancels that 1/2. For each one of them, it's going to be the same. You see that? So I can now immediately write the balance of forces in the x direction. So tangential forces, shearing forces in the x direction, S equals shear, is going to be the first one, sigma xx with respect to x plus sigma tau, partial derivative of tau y z. If you look at your previous ones, you'll see I don't have it in front of me. I can't show it to you at the same time. Unfortunately, we don't have flipping boards, and so information that I can show you at one point is limited, but you have it, I hope, in your notes. And I have the final ones, tau, what was it? I want to make sure that I didn't have a mistake. Yx, and the other was zx with respect to z. And the volume, sigma x, sigma y, sigma z. Oh, sorry, delta. I'm saying the wrong thing. Writing. Yes, please.
I think the second tau would be
Yx. Yes, you're right. Thank you. I know there was something not quite right. Yx. Yx. Yeah, they all should point in the x direction, right? Because we're just doing x direction. So now we can see similarly for the other directions what they're going to look like. In the y, it's going to be, I'm going to reorder. I'm going to write the normal in the middle here because it's y, and then I'm going to have the partial with respect to x, and this is tau x, y. Everything should point in the y direction for this second equation. Tau zy and the volume. In the z direction, I'm going to have sigma zz, and this is going to be in the y direction, and this is going to be in the x direction, and this is going to be tau xz, and this is going to be tau yz. There's a pattern there that I'm just using the pattern to complete the picture. And of course the resultant force is this is in the y direction, so the total force is going to be the one in the x times the unit vector plus the one in the y, unit vector y direction, z, unit vector z direction. So we have all of the forces that are surface forces plus the weight. Those are all of the forces that has to be equal to the mass times the acceleration. The acceleration we already calculated in the beginning of the lecture, and when we multiply by mass is rho times the volume. And you can see, I've forgotten the volume, that volume is going to cancel out from the whole equation because I have volume here and the left. So now I'm going to do, what we're going to do is force equals, for a small, we do force equals mass times acceleration. This mass is rho dx, dy, dz. The acceleration we already calculated before, so we're going to be able to now write immediately. Let's see, I can perhaps reuse some of that. No, I'm going to have to write it again. Let's see, so I'm going to write this. Rho, we had partial with respect to time of the velocity. Those are the three, in terms of a, sorry, not plus, in terms of a vector, this is a vector, and we have v dot nabla v. That was our, remember the local acceleration and the convective acceleration? forgotten the volume. Density times volume is the mass, and the acceleration is there. So this is the surface forces. This is mass times acceleration, and we have to add the weight. That's it, right? And then we have balance of forces. So I'm going to cheat a little bit, and no, I'm going to write it again. So it's going to be more neat because we have a little time. We have 5 more minutes. So all I have to do is write those, and those are the equations of motion, and we're done. That's the Navier-Stokes equations. So take a deep breath. We're going to write down the Navier-Stokes equations. And it wasn't that terrible, or was it? Was it? No? Okay. Well, you know, you're now touching the pinnacle of the mountain. So equations of motion basically are Newton's law. In each direction, taking into account the surface and body forces, weight and surface forces considered, and so let's write it component by component. In the x direction we have, let's write it down, we don't know how we've chosen our coordinate system, so let's imagine that gravity could have a component in the x direction as well. We're going to write each one has rho, this is the weight, and we don't know, we just leave it, and then it's going to be 0 when we choose our coordinate system. One is two of them are going to be 0, of course, if the gravity is aligned with one of the coordinate directions, but we'll leave it general. And we have all of the stresses. There were 3 terms, right? dx of something, dy of something, and dz of something. And each time we had the normal, so I'm writing it in a, I'm cheating, but so that we can see the pattern. This is the normal, and this is the normal, and we have now the tangential ones were tau here, this point always in the x direction, right? This is one was yx and tau zx, and this one was the point in the y direction, so tau xy, tau zy, tau xz, tau yz. Those are the all of the terms there. We only did the x direction, but we generalized, we saw a pattern, and we were able to generalize for the other components. And this in every case is equal to mass times acceleration. I've divided over by the volume everywhere, and so I only have rho times the acceleration. The first component, the u dt, plus just nabla applied to u du dx, v du dy, and w du dz. Now just applied to the second component of velocity, so it's dv dt plus, again it's u v w, but applied to v so v is always the argument of the derivative in this equation, but here we have u, v, and w each and every time. W with respect to the third component of acceleration, so w with respect to time, and again u, the w dx, v dw dy, and w dw dz. Phew! We've written out the full Navier-Stokes equations. out there. Of course, these terms were written in a way which is a little bit cryptic because it just says stresses. Now, what we want to do is relate the normal stresses to pressure and the shear stresses to viscosity. That is just the final step that needs to be done. But let's imagine first that we're looking at inviscid flow. In the inviscid flow, there are no shear stresses, and the only normal stress is pressure. So we have sigma xx equals sigma yy equals sigma zz, and it's minus p. Minus p because pressure always points inwards of the control volume. It's compressive, right? It tends to... and so we can write the equations for the case of the inviscid flow by making all of these 0. These are going to be 0 in an inviscid flow, and this one is going to be minus dp dx, this one is going to be minus dp dy, and this one is going to be minus dp dz. Inviscid flow. So for inviscid flow, we could actually write it in vector notation immediately. 3 equations together, rho times the vector g minus, you see there's the gradient of pressure in these 3 with a minus sign. These 3 are a gradient of pressure, equals to rho and the acceleration, the partial of velocity dot nabla applied to velocity, and that's it. This is the inviscid case. This is called the Euler equation. The particular case of the Navier-Stokes equations where there is no shear stresses. And even though this is idealized in the sense that we have, we don't have any shear stresses, and so it's been simplified quite a bit, it turns out that this equation really has no general solution. The reason for this equation to have no general solution is that it is a nonlinear. So if you look at this term here, this is the nonlinear term. Why would we call it nonlinear? Because we have, what is our unknown here? The unknown is velocity, of course, velocity, pressure, and density possibly. The velocity is one of the unknowns, and we have a term here that multiplies velocity with derivatives of velocity. So it's a nonlinear term. Okay, velocity multiplied with its own derivatives. These nonlinear terms make this equation very difficult. Very, very difficult to solve. There's no general solution. The only approach that you have in general is the computational approach. Put these equations, write a computer program that solves this in space and time in the most grueling way. And this is where we want to stop today. All that we're going to do next class to actually write what was on Obama's t-shirt is express the tangential stresses in terms of viscosity, and we're going to be done with the hard work. So thank you very much for your patience and your dedication today. I appreciate it.